I could have kept this theorem, but I erased. But it was the situation that we have this proper subgroup which still maps onto the image. So actually negation of it has a name. Negation of this property. So it is in the context of profinite groups, but for intuitions you can think just normal groups and normal homomorphisms. Epimorphism F between profinite groups is called Fratini cover. I will abbreviate FC if such a thing does not happen. So if for any closed proper subgroup H0, so the image is not everything. Okay. So for intuitions, you know, if you think about splitting, so there is sometimes epimorphism splits, then you get semi-direct product. And splits means that you have a subgroup here, such that when you restrict, it's even isomorphism. So it's very opposite.
What if it splits?
Okay, so splitting, okay, maybe I write it. Remark. It is intuitively, Fratini cover is opposite to splitting of F, where there is H0 in H, such that F restricted to H0 even becomes isomorphism. So in particular onto. Okay, so you can think like, yeah. So it's very, very far from this, not even partially. Okay, so something like this is kind of into this direction. Maybe not isomorphism, but still on to the smaller, closer to isomorphism. But in Fratini cover, nothing like this. So it's like a totally non-splitting thing, intuitively. And they exist. Okay, so the remark 1. So for finite groups, and actually even here there is a notion of Fratini subgroup in profinite groups as well, but I don't want to get to this. So for finite groups, F is Fratini cover if and only if kernel of F is contained in Fratini subgroup of H. And if you remember, this is either intersection of maximal subgroups or set of non-generators. Such elements that you can always remove it from set of generators. So now you can maybe see a bit of connection, because this is like, is there a clear connection? So image is onto K. So image is onto, as before, if and only if this group together with n kernel generates. Okay, so there is a slight connection with this definition, and it's true there is such a equivalence on a side. But of course we see this is our property. So corollary, just putting negations everywhere, of the previous theorem that G K is G closed if and only if the restriction map from absolute Galois group of C is KG to G understood as this Galois group is a Fratini cover. Okay, so already algebraic Galois theoretic description of this notion of G closed. And together with the last remaining property of existentially closed fields, this will actually say that it will determine this group uniquely from this group. That will be the last point to discuss. Yes, okay, is G closed if and only if this restriction map is very, very far from having a splitting. Okay, it can never have a splitting because G usually doesn't embed here Barrett and Schreier, but it's even much, much more. Examples, okay, examples of course of Fratini covers. Yes, of course, any projection from direct product from product cannot be Fratini cover, but it's not difficult to see that it is natural. Okay. If you think from the easiest, you have cyclic group of 4 elements mapped to cyclic group of 2 elements. So what is kernel is this 0, 2. You have, and there is no subgroup. Almost there is no subgroup at all, but you can quite easily see there is no proper subgroup here which maps onto it. Similarly, CPN, CP, or CPN, CPM. So those are all finite. So for infinite, and that's just in case, the p-adics to CP when you quotient, so here kernel. This is the same, or any CPN. Okay, this is an example to have in mind. Could be more general. You can take any, okay, such a thing, but what is this? You can still define it as inverse limit as Cnk, I think, but on the other hand, this is CP1, CPk. Yes, I'm saying what are n-adics? It's not a common notion, but it makes sense.
Is it a domain?
Huh?
Is the domain? Is a domain?
So I'm saying this is like n-adics, which I'm defining now. So it will be this, where n decomposes like this into product of primes. Okay, so whatever. So this is also Fratini cover.
No, I was thinking like in each Cn to the k there is a zero divisor, and I was thinking whether if this n-adix is a domain or not. As a
So by this, not.
not right.
Oh, yeah. yes, because they split. So it's like always a product. It's actually inverse limit of products and product of inverse limits. And here, okay. There are also more interesting examples. Maybe at the end I say. So here everything was commutative. Okay, at the end I will say, because it will come naturally. I mean, there are many, many more examples of things like this. So now this last notion.
Are you sure about that?
Huh?
You sure about that? This Zn is equal to Zp1 times Zpk? Because if you multiply P1 with n, then you are finding the same structure again.
Ah, yes, but kind of. But I mean, like. You mean something like this? Or not?
Yeah.
Yeah, it is true.
That is true.
So you just start your inverse system is not all the CPNs, but all the CP square n. But it's, what's the word? Like it seems like a smaller, but it's co-final or something. They approach to the same, kind of. So in the limit you get the same. This is okay, maybe not very. I think I saw it sometimes, but usually you talk about really p-adics for p prime. Just to have another example. So now this last property of ECG fields. So they shouldn't be algebraically closed, but still there is something like algebraically closed which they satisfy. And this is the remaining one, which is also model, which is studied model theoretically. So general definition about fields. A field F is pseudo-algebraically closed. Maybe you already heard. Okay, I will give definition with ideals. The abbreviation is PAC. For each n and each ideal in the ring of polynomials in n variables, if it's absolutely prime, it has a 0. And absolutely prime means it is also prime if you put alg here. So if I have alg is prime, it makes look a bit complicated, then I, meaning all polynomials from I, has a 0 in F. So yeah, so that, but that I mean ideal in F arch X generated by I. So the best, I will have several examples. So if I was principal, okay, if I is principal generated by one element, then prime means the same as this is irreducible. The element is irreducible. This is UFD. But here, it means it's not only irreducible here, but it's also irreducible in this ring. And this is more difficult to be irreducible over algebraic closure. Like if it was just one variable, then it must be just linear. So of course, yes, if I just took n equal 1, then any field would be pseudo-algebraically closed, because the condition would mean that the generating ideals are of degree 1, are generating polynomials. Okay, so I must take, and if I demand that I is prime here, then I would just get algebraically closed. Because, for example, yes, if you look at polynomials in one variable, then yeah, it would be like a contradiction. That what does it mean that ideal is prime? That is irreducible, but if it has a 0, okay, then is not to get contradiction, it is of degree 1. So it would mean that only polynomials of degree 1 are irreducible, so it is algebraically closed. Okay, so I'm just saying that this is, in this version, it is a meaningful definition, not reducing to nothing, not reducing to algebraically closed. Okay, so this is
what are we reducing?
Huh?
What are we reducing? I didn't understand the last part of this reducing part.
Okay, so it was a bit quick. So I considered two possible variants of this definition. The second variant was if I just said I is prime and didn't say that and get this conclusion. Then I argued I would just get a definition of algebraically closed field.
Okay.
And second was if I just looked at polynomials in one variable, I would get nothing. All fields would satisfy it. Okay, so some comments. Some of them I already said. Okay, it's differently stated in different books, but I think it is enough to look at, consider n equal 2. So just like looking at curves in two variables. It's not so easy, but I think one can reduce this definition to the case n equal 2. So polynomials in two variables. Okay, maybe I just say again, if you know this terminology of algebraic geometry, so if I defines some variety, then you demand the term is that this variety is absolutely irreducible. So irreducible when you go to algebraic closure, and then it should have point in the original F. So in short is that all absolutely reducible F varieties have F rational points back in F. So some example. Okay, of course algebraically, but also separately, which is less obvious, closed fields are PAC. So non-example, and this is really the problem why complex numbers with conjugation is not existentially closed. So R is not PAC. Yes, quite easy to find since this is polynomial in two variables, which is irreducible in algebraic closure, so in CX, in CX1, X2. Okay, how to such things probably you were doing. It amounts to saying that this has no second root. You cannot take a square of this and then use Gauss lemma, etc.
Wait, it doesn't have okay.
Now, I mean, as a polynomial, you cannot take second root of it. Or as a or rational function. That shows it is irreducible in Cx1, but then rational functions, and by Gauss lemma you can go back here. And of course it has no real roots, because it's positive, positive plus 1, non-negative.
X1 squared plus 1 is not irreducible in Cx1?
Yes. Is. That was argument, it is. This one.
No, I was talking about x1 squared. Let us look at x1 squared plus 1 as a constant, and x2 is as a variable, right? We were looking.
Yes, yes.
x1 squared 1, x1 squared plus 1, is it irreducible in Cx1?
So the argument was first that it is irreducible in this, in this, because this has no second root. So because it's of degree 2 and it has no roots. And then you can use Gauss lemma to see that it is irreducible also here, which is
okay, I understand.
Yeah, that's quite common.
I was trying to think about Eisenstein too. Okay, I understand.
That I don't. Okay, maybe it amounts to the same. So it amounts to saying that this is, okay, maybe it's easier, that this is irreducible. So I guess this will be a P from Eisenstein.
Yeah, but is it irreducible in this?
So again, it's irreducible because it doesn't. Okay, but this is a bit. No, but it's not irreducible. Okay. But you could take, okay, now but you could take its irreducible components and use Eisenstein. Then I think you could use Eisenstein. Okay. But then still you would need Gauss lemma at the end. Yes, I mean not Gauss lemma, but okay. Yes, Gauss lemma at the end, because Eisenstein talks about over field, not over. Yeah, okay. Okay, similar. And obviously it has no real roots. Okay, something. So first, okay, there are more PAC fields than this. So something, an infinite algebraic extension of a finite field is PAC. It's some work. It was proved by Yershoff. So all of this we discuss like this FPQ infinity. Yes, all infinite things you can find in FP-alg. All of them actually are PAC. So there are quite a lot which are not algebraically closed. And now something interesting, but the finite fields are not. But are closer and closer to be PAC. That means the ultra products are PAC. And actually the full result is, these are these Weil's formulas. So there is a theorem of X. Another one, not from the beginning of the previous series of lectures. that a field F is pseudo-finite, okay, by definition, okay, let me use to be quick ultra product of finite fields, okay, elementary. So it has the theory of finite fields. Okay, it is infinite, but has logical properties of finite fields. Okay, but this is description. Okay, so but still you can ask what are they? And the answer is if and only if three things happens. So what are these properties? They are all perfect. So if it's perfect, okay, they are not PAC, but they are more and more PAC. So in the ultra product, whatever particular condition you want to check, like this, at some point, it holds for finite fields. So actually, F is PAC. And the third one, which is also third order, what are the algebraic extension? For each n, a finite field has one algebraic extension of degree n, which actually corresponds exactly to the fact that absolute Galois group of F is Z hat. And this Axe proved, this characterizes pseudo-finite fields. So it's if and only if. Yes, we noticed that for Fp it is true, but it's also true for Fp square or any Fpn.
From right to left you are constructing an ultra product, right? From these conditions to show that it's pseudo-finite.
How did he? Conditions to show it's pseudo-finite. Okay, once I looked at the proof and I couldn't. It was long and I didn't get the main point, so I cannot. Yeah, it's not so easy to get to the main. I never understood it, unfortunately. But this is, yeah, it's very, very nice. So unfortunately for other, okay. So this notion kind of can be defined for any theory or structures, like pseudo-finite set would be infinite set, okay, easy. But pseudo-finite group makes sense, but there is no description like that. I mean, it could be, but nobody found it. Some nice properties which you list, and then you know they are quite mysterious. Okay, it's also the fact that they don't have model companion, but I don't know if it's related. But somehow the pseudo-finite groups are kind of mysterious as existentially closed one are. But maybe there are no connection between the two mysteries. That I don't know. But anyway, but here the situation is really great. There's beautiful description and PAC is used. So that's another instance. What is PAC? And finally, there is also a result that any algebraic extension of PAC is PAC. So you can take algebraic extension of pseudo-finite field, which is not. So it's a bit like this Yershov, because here you can take algebraic extension, it would like kill a part of this, like some periodics appearing here. So it will not be pseudo-finite anymore, but still PAC. So you can see there are quite a lot of them, but maybe not so easy to find a particular one, like these ultra products. Never know what they are, but they exist. Okay, so now the theorem. So now I'm not giving any proofs anymore, but it was not so difficult. So if K is EC G field, then KG is PAC. was the C as well. Okay, actually, and this is more general. Okay, this is more general. So okay, let me tell G finite. But it also holds definitely for finitely generated groups. For infinitely generated, there is a problem which I was often forgetting about. If G is not finitely generated, this is not definable. Okay, because it's finitely generated, you can just say the generators, but infinitely, so really then it's hard kind of to use it. Because, I don't know, actually, I was thinking. In the particular cases I was considering, it was always PAC, so I don't know counterexample, but there is no argument. Okay, another theorem that now this is enough, but still G finite. So G field is EC. Okay, if and only if these four things happen. So G field K perfect, K strict, K G closed, and C PAC. So that's the full description. And the other case, so the other direction, to do it like this, it uses some model theory of PAC fields, that they have some nice properties which allow to pass.
Yeah, I mean to axiomatize it, right? I mean, how do you axiomatize a PAC field?
That's another thing, whether they are first order. Okay, so this is, okay, it is known to be axiomatizable. Okay, basically there are bounds, so it is definable to say, okay, so this I, it has finitely many generators. These generators have some coefficients, and it's definable in these coefficients to say the ideal is absolutely irreducible. It is not obvious, but it is true. And then you can...
From X theorem, we can understand that this class is closed under ultra product.
Yes, as well. Okay, also G closed. This is also axiomatizable. Also, you have to think a bit, but for G finite, so basically it is saying that if you have a finite, okay, if you have a finite field, so finite field extensions of K, you may think they live on the vector space K to the n, so you can, and then the G group action also you can say is given by some linear functions of a constants. So some very, very, very long sentence for all possible degree of extension. And then you can axiomatize it. So this is, okay. But we actually found also other axioms which are geometric, but this is something which we call like Galois axioms, giving kind of Galois theoretic properties. Okay, so axiomatizable, so this is LG theory, which we call GTCF. So this TF stands for transformal fields, and this stands for transformally closed fields. And this is model companion. Huh?
Where is transformer coming from?
So there are two names. If you have field with automorphism, it's either called difference field or sometimes transformal field. Okay, difference comes from the fact that actually if you're on Kx, there is this automorphism x goes to x plus 1, and then kind of like differential. Okay, differential is the limit. What? X fx plus h over h, and this is just fx, let's say minus fx plus 1. So it's like there are differential equations and difference equations. They were classically studied. Okay, so it comes from these difference equations. But the problem is just it's hard to put D because usually D is reserved for differential. Like DCF already exists and it means differentially closed fields are invented. Okay, so this is the theory, and these are the properties. So one last thing that actually, okay, I could say more. Okay, I can say a bit. So one of the properties of PAC fields is that absolute Galois groups are so-called projective. If you know what is projective module, it's a similar definition, but inside profinite groups, not modules. Like every epimorphism into it splits. Okay? And this actually implies that if you combine it with being Fratini cover, it becomes something called universal Fratini cover, which is unique. So let me just state it, that corollary of some properties. So it's not only Fratini cover, this restriction map, but actually a unique one. So that's the way you get this absolute Galois group from G. So if K is ECG field, then this restriction map, and C is KG, then the restriction map is a universal Fratini cover, meaning that for any other, yes, like all these covers here, like you have CP and CP, you can cover it further here. So actually this one is universal. So something like this happens. Still let me write it, meaning that for each Fratini cover, here we have our S, exists continuous epimorphism here, like here. And then there is a theorem that universal Fratini covers are unique up to isomorphism, preserving this projection. So this is the way, in this sense, you get p-adics additively from this group as this universal Fratini cover. Yeah, okay, it's quite like you combine all of this Fratini covers CPN to CP, take bigger, and go to the limit. Yes, obvious example. And maybe notation. So notation. note like this, it's universal. And then, of course, example ZP. Okay, so, and of course, corollary, if K is ECG field, C constants, then absolute Galois group of C is isomorphic with this, and as before, and absolute Galois group of K is isomorphic to kernel. We notice it's the kernel of the universal Fratini cover. So this is full description of the absolute Galois groups. So how far are these groups from being, how far are these fields from algebraically closed? So here it's just ZP, so not so much. Yes, if you have existentially closed CP field, it allows only these extensions of degree which are powers of P. So one could say almost algebraically close, not so far. And actually like this, you can also find pretty explicit models inside FP-alg. This field we were discussing, you can put some structure and then see these are existentially closed CP fields there you can find. So to some extent you can see them. Okay, yes, so of course the Zn S is a bit informally is Cn. Yeah, but it always exists, and I think there is some research, and it's not often obvious what is it. Like take monster group, finite, ask what is this universal Fratini cover? I'm not sure if people know. Okay, so all these strange groups also have their universal Fratini covers. Funny thing is, which is a bit unusual and useful, that always Fratini cover, maybe you know it, this Fratini group properties, Fratini cover of nilpotent is nilpotent. Which is a bit strange, because usually such group properties are about solvable. Yes, if you have kernel image solvable, everything is solvable, but nilpotency fails. But not here. It kind of preserves nilpotency. Which we use with Oslam very strongly to prove something. Turned out to be very useful. It's because, okay, I'm diverging, because in nilpotent groups you have this unique Sylow subgroups and everything decomposes nicely. So if this Fratini covers the same, and you have profinite Galois theory, so when you put things together, they are very useful. Okay, so I'm almost finishing. So maybe last thing, there are those. So it will be also examples to here. Instead of CP, you can take CP square or CP to the K, okay, product. And then what is universal Fratini cover? It is known, but now, okay. So it is like pro-P group. In this extension, you have always pro-P groups, and everything is possible. So it's actually something called, I'm always confused with the notation, like this.
Pro-P is pro-finite and P?
No, no. Pro-P group, yeah, that's okay. Pro-P group means inverse limit of P groups. So in particular, ZP is pro-P group, but it has no torsion, so it's not a P group really. Yeah, the same with pro-nilpotent, pro-solvable. Okay. So this is, for example, and pro nilpotent doesn't have to be nilpotent. We actually see here, so this is, what is it? So this is pro P, so this is free pro P group on K generators. So like F1 is just ZP. ZP is free pro P group on one generator. And it's still okay. So it's neither free nor generated by K elements. Everything is this category of not even pro-finite, but pro-P to be. And like Z hat is F just this. Okay, so Fk is just free pro-finite. So free in the category of pro-finite, but this is only free in the category of pro-P groups. So if you, for example, the universal condition will be that you have these generators here, and if you mapped them any way you like to another pro-P group, it uniquely extends to continuous homomorphism.
What's F2 hat?
Huh?
What's F2 hat in here? Free pro-finite, but for 2.
Is there any two? Sorry?
Do you know what is the structure of F2 hat?
Not extremely. I don't know how to describe it. So for instance, let me just say, this is pro-P, this is pro-nilpotent, but the actual free group embeds here as a group. So it's very non-solvable, non-anything, as pure group. Okay, so it contains free group. This is actually, actually this hat is also completion. Yeah, I think this is true. So this is really, as the name should suggest, this is pro-finite completion.
But I mean, if there is K generator, there must be onto mapping from.
But it's not really K generator, topological generators. So I said all the names are confusing. It's neither free nor it is generated by K elements. It's topologically generated. So they have K elements such that topological closure of group generated by this is everything. So here you can embed Fk here, so it will be the closure here as well, and here it's like a full pro-finite completion of Fk, and here it's like pro-P completion. I think it also makes sense. So you only look at the quotients, which are P groups, and then take inverse limit. So anyway, the one can talk about this long time, but it's just examples here of fraternity cover. If we take more, so it becomes quite complicated actually because this free group embeds. But on the other hand, okay, so it's pro-nilpotent. So it is a product of this appropriate. It's already P. Sorry, it's already P. So it's already, from the point of view of Sylow theory, it's already pro-P. So sometimes you get like Sylow subgroups of such form in this pro-finite theory. I think, yes, I think that's it. And all such things, of course, appear as Galois groups. So you have this essentially closed CPK fields, and that would be the Galois groups. And for more complicated finite groups, some other things which may be pretty crazy. Yes, so thank you, that's all of the entire lecture.